All right, good morning, everyone. Last time we did this one. So this is our charged disk. So again, this thing is solid. So this thing has a total charge of Q, radius of R. We argued that we can chop this thing up into a whole bunch of rings, stack them on top of each other. And then, of course, Gabby told us that we're going to take the radius of this guy. She ran away. As the radius of S. So this guy has the thickness of DS. So in this case, our radius then, or at least the distance r between the charge to that point was given this way. Our differential area, which is everything included inside of this ring that we drew, was given this way. And then we calculated our electric field after doing that beautiful integral, and we got this guy. Right? The only thing I did differently between what I did yesterday is here I had 1 over z, but I also had a z here. So I just fold out the z to cancel that z out front, which is why the z is over top of this. That's all we can do differently. Okay. So basically, this brings up the question of how do I know that's correct? Okay, this is our big question, right? So how do I know that at this point, this electric field is the correct one? Meaning that, did I mess up my integral? Okay, so what I wanted to do is spend a couple minutes to talk about how I actually know these things are actually correct. And the way that we usually do this is we're going to look at 2 different limits. So our first limit is going to be as, in this case, we move far away. So as we move very far, so meaning as we approach infinity away from the objects. So basically, in this case, all this means then is since I have this finite distance of z, we just want to take the limit that z goes to infinity in this case. So I want to go very far away from this object. And we'll talk about what that means in a second. But in this particular case, we want z goes to infinity. The other limit, which doesn't always work, and I'll talk about this in a second, is we want to get really close to the objects. So meaning that in this case, I want to take the limit that either z goes to 0, meaning I want to get really, really close to this object, or I'm going to take the limit that r here goes to infinity. Either one of them are the same. So in this particular case, we're either going to look at z goes to 0 or r goes off to infinity. Now, let's talk about each one of these. So what is the purpose of doing this? So what this one says is what? If I had any object, doesn't matter what the shape of the object is, if I go infinitely far away from that object, what does it look like? So if I go very far away from any object, what does it have to look like? What does it have to look like? For example, let's think about a star, right? So if you look up in the sky at nighttime and you see the stars, what do you see? You see a point, right? So no matter what shape it is that I'm actually looking at, whether this is a disk, whether it's a sphere, whether it's some oblong object, I'm going to steal whoever's water bottle this is. Doesn't matter if it's a water bottle. If I go far enough away from it, it has to look like a dot. Okay. Now, the point of this is to say that as I go far away from it, or in this particular case here, z goes to infinity, what this tells me then is that my electric field has to reduce to the electric field of a point charge, which we know is going to be what? Kq over, in this case, the distance of z squared, right? Because I'm only moving along the z axis. Okay. So this is the first thing we can do. We can check that this thing here looks like a point charge as z goes to infinity. What if it doesn't? Then I know I'm wrong. Okay. So if this limit is not satisfied, I know I'm screwed. Okay. I have to start all over again. I messed up my integral. Now let's talk about this one. So now I have some object, whether that's a disk, whether it's this object here, whether it's a sphere. Now, again, this is going to break down if I'm talking about something like this, which is a ring. Because if I go really close to the ring in the center here, I'm not going to see nothing. Which means in this case, the electric field is going to go to 0. Or if I'm talking about something like this, where I get really close to a line of charge, again, this is going to break down. So this limit only works for like solid objects. But anyways, if I go really, really close to this object, what does that have to look like? For example, we live on what type of shape? What shape is the Earth? Approximately a sphere, right? Now in this room, what does it look like? looks flat, right? So what happens then is anytime I get really, really close to an object, whether it's this object going in this direction, whether it's a table here, or if it's a disk, or no matter what it looks like, what does it have to look like? It has to look like a flat plane, right? Which means that in this limit here, my electric field then has to reduce to the electric field of a plane, which we talked about before, is actually sigma divided by 2 epsilon naught. Okay. So in this limit, it has to go to sigma over 2 epsilon naught. Now, if I'm a little bit appropriate here, I should put my directional properties on there, right? Put these things on here. Now, again, this thing is going to fail in certain cases. This one is not always true. Bless you. And examples, again, examples of this, if I get really, really close to a line, what does the line look like really, really close? Looks like a line, right? In this case, it's not going to become an instant sheet of charge. If I'm talking about, again, something that's a ring, I'm in the center of the ring, I get really, really close to the center of the ring, I'm just going to see empty space, right? So it depends on the shape of the object. But basically, the point is that what? If I come up with an electric field, I can easily determine if that electric field is correct if it satisfies both of these two limits. If it doesn't, I'm wrong. I got to go back and do it again. Okay. Again, this one is not always true. Depends on the shape of the object. But this one always has to be true regardless of the shape of the object. What's up, Brandon? False. So if I'm dealing with something like, for example, this guy here, or if I'm dealing with something like this, as I get really, really close to it, again, it has to look like an infinite sheet of charge. So as long as it's like a solid object like this guy, then both of these limits have to be true. If I break one of them, it's wrong. Okay. But again, if I'm talking about something like a line of charge, or if I'm talking about something like a ring, in that case, only the first limit is going to work. Because the second one would just look like either a line or empty space. So let's use those ideas on this guy here to make sure that this thing actually works. So again, I want to make sure what it is that I spent my time on actually makes sense. Okay? So let's look at the first limit first. So in this case, we're going to take our z goes off to infinity. So let's look at this guy. So we now know that's what our electric field is then going to be equal to the limit as z goes to infinity of then 2 pi k sigma times 1 minus z over the square root of then z squared plus r squared. Now, at first, if I look at this, I'm going to end up with what? Z becomes very, very large. I can ignore the r squared. So the bottom portion here is just going to become the square root of z squared. But what's the square root of z squared? It's just z, or actually 1 in this case, right? So z over z, which is 1, which means I'm going to get a 1 minus 1, which means this thing is going to go to 0, right? So if I simply take this, in this case, at face value, I'm not going to get this. I'm going to get 0. Now, what I want to make sure is that I don't do something like that, which means that we're going to have to do a Taylor series expansion. Everybody's favorite thing. So let's talk about how this is going to work. So first thing I'm going to do is I'm going to factor z out of both of these two terms. So here I'm going to factor out my z, or my z squared in this case. So let's take the limits as z goes to infinity of my 2 pi k sigma. And I'm going to pull out a z squared from here, which is going to kill off this z. So I'm going to get a 1 minus 1 over 1 plus r over z squared square root. Is okay? Now, in this case, since z is going to infinity, r is a finite constant, what is this term going to go to? It's going to go to 0, right? Which means that we want to do a Taylor series expansion about this particular term here. Okay? Because I want to see what is the leading behavior of this thing, not the fact that it just goes to 1. Okay? So in this case, we have to use our Taylor series expansion. So I'm going to define x as r over z. So this is going to be my small parameter, which means that I want to Taylor series expand something that looks like this. Okay? Now, anybody remember their Taylor series expansions? It's been a while. So the one that we're going to be most interested in is this one. So I'm going to take my 1 plus x raised to the nth power. This is my Taylor series that I want to look at. Now, under Taylor series expansion, this thing is going to become equal to 1 plus n times x. Okay. So this is my Taylor series of this guy. Now, in this case, what I have is the square root of 1 plus x squared. So in this case, this is the same thing then as 1 plus x squared raised to the 1/2 power. Or in this case, we have a 1 over that, so this is going to become a negative 1/2. Okay? Now, following this logic here, I can always define a new variable, x squared. I can call it y. Right? It doesn't really matter. So using this guy here, this is going to be approximately equal to 1 minus 1/2 x squared. Is okay with that? So using this definition of my Taylor series, you can look it up if you want to. This thing here is going to become this. Okay. Now let's plug that into here. So this guy then is going to become equal to then, get rid of these, the limit as z then goes to infinity of 2 pi k sigma. I'm going to get a 1 minus x squared over 2. Okay. Let's close out my brackets. Put my k hat on. Sorry, Omar, I don't know if you can see that. Okay. Now, what happens to the ones? They're going to cancel, right? And I'm going to get a minus and minus. That guy's going to become a plus. So let's put everything together. So finally, what I'm going to get is that my electric field then at point P is going to be the limit as z goes to infinity of then what? 2 pi k sigma times x squared divided by 2. Is okay? What happens to my 2's? They cancel. So sure to that. This is going to cancel. And again, we define x as what? R over z squared. So this thing then is going to become equal to then what? Pi k sigma r squared over z squared. And of course, I'm always dropping my k's. Now, in this case, I'm going to drop the limit portion because we've already taken the limit. Okay. Now, let's take this a little bit farther. We also know that sigma is the same thing as the total charge per total area. Get rid of this. But we know the area of this is simply that of a disk. So this is going to be q over pi capital R squared. Okay. Now let's plug that guy into here. So this is going to become what? Pi k q r squared over pi r squared z squared in the k hat direction. Everybody's okay? What happens to your pi's? They cancel. What happens to the r squareds? Also cancel. So that's going to cancel with that. That's going to cancel with that. And finally, this thing then is going to become kq over z squared, k hat direction. What is that? It's a point charge, right? So in this limit number 1, this thing is satisfied. It looks exactly like a point charge. So far, I can be pretty happy this thing is true. Okay. Now let's look at the other limits. Let's do the other limits. Cool. So my other limit then is, let's go back to our original electric field. So my original electric field again is EP is then equal to 2 pi k sigma times 1 minus z over the square root of z squared plus r squared in the k hat direction. Everybody's okay? So in this case, what we want to do now is check the limit that either z goes to 0 or r goes to infinity. They're the same thing. So let's take the limit that r goes to infinity. So I want the limit as r goes to infinity of then 2 pi k sigma 1 minus z over the square root of z squared plus r squared in the k hat direction. It's okay? Now, when when r goes to infinity, what happens to this term? Goes to 0, right? So in this limit, this term simply goes to 0. So I'm then going to get 2 pi k sigma in the k hat direction. Okay? Now, we also know what? What we want is the electric field to look like sigma over 2 epsilon naught. Now to do that, all I have to do is remember that K is equal to 1 over 4 pi epsilon naught. So let's use the definition of K. Plug that in. So I'm going to get a 2 pi sigma divided by 4 pi epsilon naught, all in the K hat direction. Okay. What happens to my pi's? Cancel. This is going to make this guy a 2. This guy then becomes what? Sigma over 2 epsilon naught in the K hat direction. Also satisfies the lower limit. This thing is true. Okay. So again, do you have to do this? The answer is no. But if, again, you want to make sure that what you spend, say, 20 minutes on actually makes sense, then I would do these two limits. Right? So again, what has to be true is when I go infinitely far away from an object, it has to look like a point charge. If it does not, you're wrong. If you get infinitely close to a solid object, it has to look like a sheet of charge. If it doesn't, you're wrong. Okay? Now, again, if you satisfy one of them but don't satisfy the other one, you're wrong. Right? Easiest way to know if what it is that you did actually makes sense or not. Okay. But again, the second one here is going to be not always true. Depends on the overall shape of the object. But again, this thing has to be solid. As long as this thing is a solid object, this is always going to be true. Okay. Now, again, am I going to ask you to do this on an exam? No. If you did not, if you actually did it on the exam, I'll probably get all kinds of super excited and give you more points for it. I feel like I accomplished something in my life. Was okay? So good. So all I want to do is show you that. So let's do one more example of this integration stuff, and then we'll move on to other quantities and other things to talk about. So let's do one more example. Example here is up on the screen. So it says, we want to know what is the electric field, some distance z, for example. It says r in this case, so we'll do r. Some distance r above the center of a thin, finite length rod of length L with a total charge of Q. So here's my rod. Okay, so here's my rod. And above the center, so this is about the center points here. So this is my distance of r. And then this thing has a total length to it of L. Okay. So our point P here is this point. This is the electric field point that we're interested in. Now, when I say a very thin rod, even though I'm drawing this thing kind of thick, what I really mean is it's just a line. That's it. So a line of charge. But in this case, I'm going to draw a little bit of thickness. But again, we're not really talking about something like this. We're talking about something that's infinitely thin. Okay, that's what we really mean in this case. So that means we don't have to worry about the width of it. Okay. So cool. So let's go through all of our stuff that we did yesterday. So we know the electric field at point P is going to be what? K integral dq over r squared in the r hat direction. Now again, to do all the steps we did yesterday, we're going to draw a representative amount of charge here. So this is going to be my dq. My r then is going to be the distance from dq to the point of P. So this is my r, which means that in this case, my electric field from this guy, assuming this guy is positive, would point away in this direction. So it's going to be my differential electric field in this direction. Now, again, the next thing I want to do is look for symmetry. Do I have a symmetric point on this side? Yes. Right. So here I would choose my symmetric point. Here is my dq on this side. Again, I would draw my r. So this is my r in this direction. A little bit better. There we go. There's my r. My differential electric field in this case would point this way. Again, what's true about the length of each one of those? They're the same, right? Because this distance here is the same as this, same as that, which means what happens to the horizontal pieces? They cancel, great, which means my total electric field is only going to point just like the other cases in this direction. So this is going to be my ET. Now, Jamie yesterday asked a fantastic question. Is this always going to be true? The answer is, again, no. So for example, if I took this as my point P, and now I choose this as my, say, dq, so this now becomes my r, is there anything symmetric on this side? No. So in this case, since there's nothing symmetric on this side, what would end up happening then is my total electric field in this case would point off something in this direction. Okay? which means now my electric field becomes two-dimensional, which means in this case, my total electric field, or this guy here, would then be equal to the x component in the I hat direction of the electric field at point P, plus then the y component of the electric field at point P, j hat. So in this case, what you would have to do is actually do two separate integrals and then vector sum the results of those two separate integrals together. Okay. So anytime I don't have perfect symmetry, it's always going to be multidimensional, which means you have to do two separate integrals using this integral. Okay with that? But in this case, we have perfect symmetry, so we don't have to worry about that. Next part is, let's define our angle. So my angle in this case, I'm going to take this angle here as my angle theta, which means that this angle here is the same as this angle. Since my total DE points in this direction, but I actually only want this portion, so which portion of my integral do I want? So I want this portion here. So is that the adjacent side or the opposite side? The adjacent side. And which trig term goes with the adjacent? The cosine, right? So this thing is going to become K integral dq over r squared cosine of theta in the k hat direction. So let's call that my z direction for funsies. Take this as my z direction. And then I'm going to choose another coordinate system here. So I'm going to call that my x direction, just for funsies. So we have something to identify it with. Always okay? Next thing, let's define this distance here as my distance x. So that's going to be my distance x from the origin, which in this case is at the midway point, to the location of dq, which means r in this case is going to be the square root of x squared plus capital R squared. Okay. Now again, we're not going to use this angle here, but we're going to use this angle here to rewrite cosine in terms of the geometry, which means according to this angle, we want the adjacent side, which is capital R, divided by the hypotenuse. So then cosine of theta is going to be capital R divided by my hypotenuse. Okay? Now, before we move any further, what type of symmetry does a line have? Line symmetry. Amazing how that works, right? So my line symmetry then, so I'm going to rewrite my dq as lambda dl, right? Where again, lambda is going to be constant in this case, which is going to be q over L. We'll use that in a little bit. Now, dl, as we talked about many times yesterday, is going to be the length of this small section. This is my dl. Now, however, I have defined this axis as my x-axis, which means how could I rewrite dl in terms of x? Just dx, right? So in this case, dl is the same thing as simply dx. So it's going to be the same thing then as lambda dx. So good. Let's put everything together now. So now I'm going to have k. Lambda is a constant, so I'm going to pull it outside of my integral. Integral of r dx over x squared plus r squared to the 3/2 power, all in the k hat direction. Was okay with that? So all I did here is I replaced this guy with r over r. So it's becoming r cubed. That's where that top r comes from. Okay. And again, then I'm just using this guy as my, without getting, yeah. Oh, because I'm just slicing a small section, in this case, of the x-axis. So dl is the width of this small slice, but since that's along x-axis, then the width of that is equivalent to the slice along the x-axis, so that would be dx in this case. Okay. Is that okay? If I call this the y-axis, it would be dy. Okay. So it just depends on how I define the axis. But in that case, the small slit or width that I cut this thing is the same as what it is on that axis. And in the other example was like, because in that case, they were usually circular. Exactly. Exactly. So in that case, we had to worry about arc length, basically, what I was doing with the ring. Exactly. So in that case, my x-axis went this way. So it wasn't only along the x-axis, it was x and y. So that's why I couldn't do it in that case. Absolutely. Good. That was okay. Now, the last thing is we always have to integrate over where the charge actually exists. The charge only exists on the rod itself. Now, according to this coordinate system, if this thing has a length of L, this is my origin. What is my lower bound? Negative L over 2. And what's my upper bound? L over 2. So I'm going to integrate this thing from minus L over 2 to positive L over 2. Last thing is, and only integrating along the x-axis, which means it's independent of the distance r. Right? No matter where I am along here, that's irrelevant as far as I'm integrating along the x-axis. So r here is also going to be a constant. I'm going to pull it out. So finally, we're going to get that our electric field at point P is k lambda r times then the integral of minus L over 2 to L over 2 of dx over x squared plus r squared, all raised to the 3/2 power in my k direction. It was okay? Now, things to point out about this one. This one, you cannot use the U sub. Use the U sub, I would need an X on top like we had yesterday. In this case, I don't have an X on top, so U sub is not going to work. Integration by parts is also not going to work. Anybody know how you would actually solve this mathematically? Go ahead. You could do that, or trig sub. You could do either one. In this case, trig sub is a little bit easier. Since I have this plus sign here, you would actually use the tangent. In this case, we're not going to do that. We could. It would take a little while, but I'm not going to do that. Just note, this is not a U sub. This would be a trig sub. Okay. Now, as far as the exam is concerned, all you would do would be set this up, flip to the front page, and then write down what the solutions. So let's pretend we're doing it. So it turns out that the solution of this integral, so if I have the integral of dx over x squared plus r squared 3/2 power without the bounds, this works out to be x divided by r squared square root of x squared plus r squared. So this is the solution, or what this integral actually becomes. So cool. So let's plug that in. So this thing now is going to become k lambda r times this guy. So I'm going to get an x divided by r squared times the square root of x squared plus r squared, evaluated from x is equal to minus L over 2 to L over 2 in the k hat direction. So finally, all we have to do is stick in our bounds and then solve from there. So let's do that. So my electric field at point P then is going to be k lambda r times. So first I'm going to put in the upper bound. So I'm going to get an L over 2 divided by the square root of L over 2 squared plus r squared. Subtract then off the lower bound. So I'm going to get a minus L over 2 divided by the square root of minus L over 2 squared plus r squared, all in the k hat direction. What's that again? Where did it go? Oh. Yeah. Thank you. Good point. So this one's going to cancel with that. You know I like to forget things all the time. That was okay. So from here, finally, I would find this. So does this negative here matter? No, it's squared, right? So this denominator is actually the same as this denominator. And then I'm going to get an L over 2 minus a minus L over 2. But what's L over 2 minus a minus L over 2? L. So at the end of the day, this thing is going to become k lambda over r times L divided by the square root of L squared over 4 plus r squared in the k hat direction. Finally, we do one more step, which is use our definition of lambda, which is q over L. So that's going to cancel this q. And we're going to get a kq over r, 1 over the square root of L squared over 4 plus r squared, k hat direction. Okay? Now, again, as far as the exam is concerned, this is exactly what I want you to do. The physics ends here. So the physics is setting up the integral. Again, knowing what dq is, knowing what r is, what type of symmetry do you have, how do these things cancel each other, what direction does it point in, do I get a cosine, sine, etc. From there, you would switch to the front page, copy this guy down, i.e. put this in here, evaluate it at your bounds, simplify, and get this guy. This is what I want you to do on the exam. So again, if you want to do U sub, if you can use U sub, you can do that, but otherwise just flip to the front page. Save yourself time. What's up, Gideon? You got your own question. Okay. We're doing okay? What's up?
Why do you keep it as the bound from L over 2 to negative L over 2, so just taking a symmetry of L over 2 0. Then.
I mean, I could do it that way. I could do it that way. Either way is fine. I could do it that way and then multiply by 2 at the end of the day. Yeah, I mean, that's absolutely fine. So either way you want to do it, yeah, you can multiply by 2 and go from 0 to L over 2, or do it this way. It doesn't matter at the end of the day. But yeah, because that's complete symmetry. The only time you couldn't do that is if, for example, if your line charge density is not constant, but if this thing went as some constant, for example, times minus x, for example. Okay. So in that case, what that means then is what? My charge on this thing, if I thought about the charge as a function of position, would actually do this, right? Or it could just be x, doesn't have to be minus x. Let me just call it x. Okay. So all that means then is what? This side is going to become negatively charged. This side is going to become positively charged, right? So what happens in that case? What happens in that case then is because this side's negatively charged, this is positively charged. In this case, your DE would actually point in this direction, which means now the vertical components would actually cancel. And in that case, your electric field would actually point in this direction, right? So in that case, you would have to actually perform the integral from minus L over 2 to L over 2. So in that case, I couldn't do that. But as long as I had something which is symmetric, so on this side, I have the same amount of charge on this side. So if this guy went as, for example, x squared, I could do that as well. So go from 0 to L over 2 and multiply by 2. So it'd be fine. Yeah. But yeah, either way is fine. Whatever way you want to do it. Was okay? Of course, that would also change the value of the integral because now I'm introducing more numerator terms and things like that. One other thing I want to point out before we move on is notice that the dimensionality of the denominator always goes as distance squared. Okay, so here I have charge on top, right? Just like the point charge as kq over r squared. This thing always has to go as 1 over r squared if this is q. So notice here that's true because I have an r here. This is the square root of a distance squared, which means that's a distance. So I have a distance times a distance, so it goes as 1 over r squared. The only time this is going to be different is if you leave it in terms of sigma, because sigma is already q over distance squared. So the distance squared is already brought into account in sigma. Okay, but the electric field always has to go as 1 over r squared. Always. Okay. I probably confused the hell out of everybody. Are we doing okay? Now again, like I said, there will definitely be a problem like this on the next exam. So let's move on. So now we've done integration, which means we talked about how to actually calculate electric fields for both point charges and for continuous charges, which means that now that we know we have the electric field, we can actually determine the force on a charged particle knowing the electric field. So the way we started everything is we said we have the force on a charged particle, and then from that force, we determine the electric field. Now let's do the opposite. So let's say now that we know the electric field, and now we're going to put a point charge inside of that electric field. So now we want to calculate the force on it. Okay. So let's go back to our definition. So we said the electric field is the same thing as the force per unit charge. But if I simply rearrange this guy, I'm going to get then that the force is the same thing as the charge times the electric field. Now, the difference is here, this says that we know the force, and then from the force, we're finding the electric field. What this one is saying is that we know the electric field, and then we're finding the force. Okay. So what this means then is if I took an object and I put it inside of a predetermined, already known electric field, we can now determine the force on any charged particle at a given location. Okay. So let's do some examples of this. Let's see how this actually works. And then we'll move on from there. So let's do another one. So this one says that, I think this is what I want. Yeah, so this says that we have a charged particle of mass m in charge q enters a region between two charged plates, each of the same magnitude, however, an opposite sign, initially moving parallel to the plates with some initial velocity v0, let's call it. So I want to know by how much will the charge deflect when the charge exits the charged plates. Okay, so let's draw our picture. So cool. So it says I have two parallel plates. So here's one plate, here's another plate. One of them is positively charged, the other one is negatively charged. All right. So all along here I have positive charges, all along here I have negative charges. Great. Now I'm going to take some charged particle. Here's my charged particle. This guy has a mass and a charge, moving horizontally with some initial velocity d0. Now it's going to enter into this region of 2 points. Okay. Now again, I have a positive charge here and a negative charge here. So what has to exist inside of the place? An electric field, right? My electric field has to point from the positive to the negative. So this is going to be the direction of my electric field. So what's going to happen is by the time it enters into this region, so let's say my particle is now here, it's now going to experience a force, right? Because now we learned the force is the same thing as the charge times the electric field, which means this guy's going to experience a force in exactly the same direction as the electric field because it's a positive charge. Now, if it was a negative charge, what direction would the force be? Opposite direction, right? Because in this case, negative charge means I get an extra negative sign, which means it's in the opposite direction as the electric field. But in this case, it has a positive. Now, if it has a force, what also must it have? Well, direction. The force results in what? An acceleration, right? So we're going to have an acceleration down in this direction. Okay? So what's going to happen then is this thing is going to be moving in this direction, but it's going to feel a downward force, which means what's going to happen to the trajectory of the object? It's going to curve down, absolutely. So this thing then is going to do this, okay? Which means basically it's going to move under projectile motion, okay? So what I want to know is by the time this thing comes out through the plates, by how much has it deflected from its original path as it entered in? This is what we want to know. What is that deflection? Now, in this case, we also know that this is parallel plates, which means that what? This guy's going to have an electric field, which points this way. This is my positive. We're also going to have a negative electric field, which also points towards him, which means my total electric field on the inside, total, is going to be the same thing as the positive electric field plus the negative electric field. Okay? In this case, this is all going to be in the downward direction, which I'm going to call that as my positive y direction. So this is in the j hat direction. Now, what I also know is this is a parallel sheet, and we already said that the electric field for a sheet of charge is the same thing as sigma divided by epsilon naught. Okay. So in this case, I'm going to get sigma over 2 epsilon naught plus sigma over 2 epsilon naught. So this thing is going to be the same thing as sigma divided by epsilon naught in the j hat direction. Okay. So this then is going to be my total electric field. Now my force then is going to be the same thing as the charge, which in this case is capital Q, times the electric field. So that's going to be the same thing as the charge times sigma divided by epsilon naught in the j hat direction. Okay. Now nothing here is spatially dependent, which means this is a constant force. From there, we know by Newton's second law, this is going to be equal to ma, which means my acceleration then, or at least the magnitude of the acceleration, is going to be sigma over the mass times epsilon naught. Okay, so this is going to be my acceleration. Everybody's doing okay? So from there to get my deflection, all we have to do now is look under projectile motion, which means we're going back to kinematic equations. So we're going to write down a x direction, and we're also going to look at a y direction. So the x direction, we know this guy's going to be x is equal to x naught plus v naught times t plus 1/2 x acceleration times time. And in y direction, we're going to y then is equal to y naught plus v naught y times t plus 1/2 the acceleration in the y direction times time squared. Just starting off with our second kinematic equation. Now, whenever I'm dealing with kinematics, what do I need? A coordinate system, fantastic. Reinhard, what coordinate system are you going to take? X and Y, good, I already defined Y downward, and you want X to go to the right or to the left? To the right, and where do you want your origin to be? Right, but when? So when it first enters, when it exits, where do you want it to be? Like when it first enters? First answer sounds good. So let's take this as our x direction, and this is then our y direction. Okay. Now, according to Reinhard's coordinate system, what is the initial position in the x direction? 0, right? What is the initial position in the y direction? Also 0. Good. Is there any velocity initially in the y direction? No. So this term is going to be 0. Is there initial velocity in the x direction? Yeah, whatever this is, v0, right? Is there any acceleration in the x direction? No, but there is an acceleration, which is this acceleration in the y. So this guy's going to be the same thing then as v0t, and this guy then is going to be equal to 1/2 a t squared, where this is my a. Are we doing okay? So let's look at the y direction first. What the y direction says then is what? We can find the deflection, which is equal to 1/2 the acceleration, if we know the time it takes to travel the plates. Right? So I can find this amount of deflection if I know the amount of time it takes to travel the plates. At the moment, do I know that time? No. Where's it going to come from? It's going to come from the x direction. So let's say my plates have a length to them of L. So in this case, we're going to take L then is equal to the initial velocity times the time. Right? So this is the time it's going to take to travel that total distance of L. Okay? From there, we can solve for the time. So time then is going to be the same thing then as L divided by V0. Now, let's plug that guy into here. So my deflection then is going to be 1/2 A times L squared divided by V0 squared. Finally, we know L is this guy here. So let's plug that in. So it's going to be the same thing then as what? Q sigma over twice the mass epsilon naught times the length squared divided by the velocity squared. So this then is going to be my deflection. It's okay? Not bad. Pretty straightforward. Let's do another one. So this one says that we have a ring of charge. So here is my ring of charge, bless you. So here's my ring of charge. Beautiful. This guy's going to have a radius of capital R. And we're going to put a charge particle in here. Let's say this is an electron. And this thing has a total charge of capital Q, which is positive. We're going to put this guy here. Now what we're going to do is we're going to displace that charge some amount of z along the central axis here. So this is my z-axis. And we want to know what happens to this charge particle. What happens to this? This is my next problem here. Problem 14. So what's going to happen to this charge particle? I mean, it's told you on the board, but let's pretend we don't know. What's going to happen to it? So to kind of motivate us a little bit more, let's write down the electric field of the ring that we came down with yesterday. So we know that for the ring of charge, we found that the electric field at some points P was equal to, so this was 1/4 pi epsilon naught Q times Z divided then by, where am I? Z squared plus R squared to the 3 has power, in this case, in the K hat direction. Okay? So what's happening in this case then is at this point, this guy is going to feel, at least the electric field is going to point in this direction. But because this is a negative charge, what's going to be the direction of the force? It's going to be downwards, right? So in this case, the force on it is going to be in this direction. Okay? Which means that when this thing is here and I'm going to displace it some distance of z, this thing is going to be what? Attracted back to the center. Okay, so it's going to have an acceleration towards the center. So it's going to accelerate. Now, by the time it gets to the center of the ring, according to that, what's going to be true then about the electric field at the center of the ring? When z is equal to 0. So according to this, what's the electric field at z is equal to 0? 0, good. So if the electric field is 0, what's true about the force? Also going to be 0, which means this thing is going to feel an acceleration. speed up, speed up, speed up, speed up, hit the center where there's now zero acceleration, which means what's true about the velocity? It's going to be maximum, and then it's going to move to the other side, and then what's going to happen with the force? It's going to be equal and opposite in this direction, so it's going to slow down, stop, and then what? Harmonically oscillates. Told you I'd never let that go. Okay? So we want to know then, according to this problem, what is the angular frequency? Or in this case, it wants us to show that the angular frequency is given this way. So let's do that. Let's do that. So what do we know? So we now know that's what? The force is going to be equal to the charge times the electric field of the ring, and that's going to be equal to the mass times the acceleration. It's okay? We also know that this is going to point in the negative direction because we have a charge here of the electric charge. So this is going to be minus the electric charge, which is the fundamental charge, times that electric field. So it's going to be 1 over 4 pi epsilon naught, charge of the ring times the distance z, divided then by z squared plus r squared to the 3/2 power, all in the k hat direction. And that has to, by Newton's second law, equal the mass times the acceleration. Anyways, okay? Now, going back to harmonic oscillation, we know we want the acceleration to always be equal to minus omega times the distance of x, or in this case, since we're looking at the z direction, we want it to look like this, right? Minus omega squared times z. So I want to make this guy look like that guy. So we're going to do that by dividing by the mass. So my acceleration then is going to be equal to minus e 1 over 4 pi epsilon naught mass q z over z squared plus r squared 3/2 power k. Okay? We're almost done. Now, comparing this guy to this guy, we have the negative sign. We have z, but just like we did in that problem that we did, at the beginning of the week, we have this pesky z in the bottom here. We have to get rid of this guy to make it look like this guy. Now, where that comes in is, as it says here, we're going to look at the limit where z is much, much less than r. So that means we're going to only disturb this or pull it away from the origin by an amount of z much, much less than r. Now, as we talked about before, if z is much, much less than r, do I care about z squared? No. So this z squared is basically just going to go away. This is going to become a r squared to the 3/2 power, which is the same thing as r cubed. So let's put that in. So finally, I'm going to get a minus 1 over 4 pi epsilon naught mass. And I'm going to get my EQ over r cubed times v in the k hat direction. Okay? Again, matching this guy to this guy, negative sign is the same. The z is the same. So now anything which shows up, i.e. here, is omega squared by definition. Okay? So simply reading off at this stage and taking the square root, what we finally find in this case then is that my angular frequency is going to be the same thing as EQ over 4 pi epsilon naught mass r squared, r cubed, square root. This is my angular frequency. Okay? Not too bad. Right? So again, all this basically says is, as long as I know what the electric field is, I can find the force on a charged particle by putting it into this electric field. That's it. Now, what I would also guess is that this will also be a question on the exam. Okay? So basically, we have 2 more topics to talk about in this chapter, and we'll finally be done, and then we can start moving into things like Gauss's law. Now, one thing I will warn you is Gauss's law is practically easy in practice, but it is conceptually difficult. We may start that tomorrow. If not, we'll definitely do it on Monday, which means by the time you come in, when we start Gauss's law, I want you to have your thinking hats on. Okay? I'm going to ask a lot of questions. We're going to go through it. Again, it's going to look ugly. It's going to look scary, but there's a point to it, and we'll talk about that. The point is to make it as easy as possible. Okay? So, I'll see everybody tomorrow. Have a fantastic day. I got stuck on the voice.